Okay, today we are going to finish the last part of the DRAM. So this is like an overview of today's memory system between the processor and the main memory DRAM. And here we have the processor, like your CPU or GPU. Then you may have the SRAM for your cache. And then we have the data bus. And here, for example, the memory controller can be built on the CPU stack, and then we have the data bus connecting to your DRAM stream. So this is a very representative design of today's memory system. And to move forward, so here we want to have the high bandwidth memory. So we discussed last lecture that we can stack multiple DRAM dies vertically using the TSV plus the micro bump technology. So basically you can have the vertical connections between multiple dies of the DRAM, and then you can have this kind of a DRAM memory cube, and then this is sitting on top of the interposer. So here the substrate here is the silicon interposer, and you have some horizontal connections between the CPU die and the DRAM stack. So this is also widely used today for high performance computing platforms. And then if you project to the future, so we can have a truly vertical stack, because still in this one you have the processor and memory separate out in a two-dimensional space. So this is more like 2.5D integration, because in this case the memory stack is already vertical 3D, but the processor die is still on the 2D space. So the true 3D is to put the processor's die directly underneath the memory stack. So in this case, so we want to have the processor's die directly sit underneath the memory stack. And this can enable the largest bandwidth, because now you can have the vertical connections between the memory stack and the processor stack. So you can have many layers through this TSV technology. And this one is not realized yet in the volume production. One of the challenges will be the thermal heat dissipation. So when you have the, let's say, the processor underneath the memory stack, because the processor, as you do the active computation, then you generate the power, dynamic power from your logic circuit. Then the processor may become very hot. If you put the processor directly on top of, underneath the memory stack, this heat is difficult to dissipate, unlike this one. So this one you can have the like your thermal conducting material covering the processor, so then the heat can be dissipated easily. But if you hide the processor underneath the memory stack, then this heat may cause some troubles for the memory. Let me ask the question. So what kind of potential problems you may have if you have the heat generation underneath, if this is a DRAM stack? So any idea? So the DRAM may degrade in certain aspects. So what aspects may the DRAM degrade? Any idea? If the temperature goes up, so one of the DRAM's challenge would be the leakage, right? So here we've got some answers from the chat. Yes, higher leakage. So your data retention may become even worse if you have higher temperature. So that means we have to develop the thermal Radeon material. So if you have a very good thermal conductivity between those tiers. You can spread out the heat from the center of the die to the edge. Then you can envision this kind of a true 3D stack in the future, but this is still under research. Okay, so if we extend the concept of the heterogeneous 3D integration to a wider spectrum, then we may envision this kind of a heterogeneous platform. So not only the memory, like DRAM, can be stacked on top of the processor, you can also use the TSV and microbump technology to stack different chips on top. So you can further have the flash, NAND flash on top, and also you may have some analog chips, for example, your RF or even MEMS for the sensor and actuators. So you can have a truly integrated system on this 3D stack. So this is the future of the system integration using the TSV technology. But again, the heat dissipation is a potential problem. But as you may notice that across those stacks, the CPU should be the hot spot, because as you do the active computation, then the CPU will have higher temperature than other stack. Okay, so then let's talk about the HBM in more details. So the HBM is high bandwidth memory. This is used to refer to the DRAM stack that are vertically integrated through the TSV and microbump. So here we have shown this kind of a schematic before. You may have the processor like your CPU and GPU, and then they are sitting on top of this silicon interposer, and then there may be some horizontal connections. And on the other side, this is the HBM stack. You have multiple DRAM dies, and then between the DRAM dies, you have the TSV to make the connections. So this is like the cross-sectional view. And then this is some real image under the microscope to show the TSV stack. And also this is from the top view. So from the top view, you may have the DRAM banks. Those are the DRAM banks. And in the middle, you will have this TSV array. So there you may have many of those vias. So here the motivation for the HBM is to achieve the highest bandwidth. So the HBM stack may achieve like 1000 gigabyte per second bandwidth. So this is a very high bandwidth, and we will show some comparison with other interface protocol. So here we can have a comparison for a system design, and this is from Samsung. So here imagine there's a processor, probably like your GPU. You can equip the GPU with either GDDR5 DRAM or the HBM. So those will be on the same interposer. You can have the GDDR5 or the HBM. So here you can have 8 gigabit GDDR5, and you have 12 of them placed around the processor's core, or you can have 4 of those 4 gigabyte HBM stack. But you look at the form factor here, because the HBM stack, you stack the DRAMs vertically, so the form factor in terms of the total interposer area can reduce significantly by 75% from this 3000 millimeter square to like close to 800 millimeter square. And total chip density in terms of this is the DRAM capacity. So for this design, it's like 12 gigabytes, and you can have even more bits in the HBM stack, 16 gigabytes. And the bandwidth, this bandwidth is the total system's bandwidth. So in this GDDR5, you may only have like 300 gigabyte per second, but for this one, you can get like up to 1000 gigabyte per second. And also the power is reduced, so all the specs get improved. So the key enabling feature of HBM is the I/O bandwidth, not I/O bandwidth, I/O data width. So here, this is critical. So the last row here for the GDDR5, the number of pin is 32 per chip. So here, this chip will give you 32 bits simultaneously through the GDDR5 interface protocol, as we discussed before, the DDR interface. And for GDDR5, it's 32 pins per chip. And then you have 8 of those. So in total, you have the data width, the data bus width, like 384. And then for the HBM, the reason it can have the higher connectivity here, for example, each HBM stack can give you 1024 pins per cube. So if you think about this HBM, you have this stack. So the last bottom die will give you 1024 bits simultaneously. So that's 1024 actually pins. So in this case, the pins are distributed. If you look at the top view, because you have the TSV, so it goes through the silicon substrate. So you can have those pins distributed across the whole chip. Therefore, you can have many connectivity. But in the traditional design, the traditional chip, the connections are coming from the pad. A pad is, on a 2D space, and normally you have this pad at the edge of the array. Normally you may have the pad at the edge of the array. So then that is very limited in terms of number of pins for the traditional design. So that's why here you can have more connections, and you have 4 of those HBM stack. So in total you have 4096 bits transferred simultaneously. So basically you have more lanes in your highway. If you make this analogy to the highway system, then you have more lanes for the HBM. So this is a key to improve the system bandwidth. Any questions so far? You mean the bandwidth here? You mean for GDDR5, why is the bandwidth 384? So here you have to look at individual bandwidth per bit and then multiply by the number of pins you may have in total. So here, so I think maybe in this case, even though you have so many pins, not every pin is used simultaneously. So for the GDDR5 case, because I think the GDDR5, the bandwidth per pin is larger than 1 gigabyte per second. So here it seems that they didn't use those 384 pins simultaneously. But anyway, this number is at the system level. That is what the processor can fetch from the DRAM system. This is the bandwidth for the total memory channel. So here the HBM was first introduced by AMD for the products of the so-called Fiji Chip. So this is a GPU, and this is the first GPU that integrates HBM. This was like a few years back, around 2000, maybe 16 or 17, around that time. So here, in this case, this is a GPU, and then it has 4 GB HBM, and in this case, 4000 bit wide interface. And then this is total memory bandwidth for the system. And then later, for all kinds of high-end GPU, the HBM becomes a must. So it becomes a default settings for the GPU. For example, Tesla V100, this is one of the high-performance NVIDIA GPU used for like machine learning, deep learning acceleration. And this one equipped with either like 16 GB or 32 GB HBM2, and this one reached like around 900 GB per second in terms of system bandwidth. So here is a general trend for the bandwidth at the system level. So here you see the first one is a DDR, and then second one is LPDDR, and then the third one is a GDDR, and the last one is HBM. So the x-axis is the bandwidth. So certainly the HBM gives the highest bandwidth. And also from the density point of view, from the y-axis, HBM gives the highest density as well, because you can stack multiple dies vertically. So here, this is the general trend. And for the applications, like the DDR, as we discussed before, is mostly for your PC and some low-end server. And then LPDDR for your mobile system, like your smartphone, tablets, and so on. And then GDDR is like your graphic, like your gaming machine, Xbox, and so on. So those kind of things. And HBM is for the high-end, like data center server for the machine learning acceleration. So any questions? Okay, so the HBM right now, of course, is the, let's say, the most promising technology for moving the DRAM to the next level in terms of the bandwidth and density. If the DRAM cannot scale horizontally to 10 nanometer load, then the only way to improve the system level performance is through the HBM by stacking more DRAM dies vertically, or make the number of I/O pins wider. Let's say have more like bits to be accessed in parallel, so you can improve the bandwidth. Okay, then the last topic for the DRAM section will be this embedded DRAM. So this is a technology that aims to address the gaps between the SRAM and the standalone DRAM. So far when we talk about the DRAM, we usually refer to the standalone DRAM. So this DRAM, if we didn't specify anything, so by default, it means standalone DRAM. That means it's off the chip. So you can have those DDR or GDDR or HBM. Those are all off the chip, off the processor's chip. So it's on the separate die with the processor. Here we are going to discuss the eDRAM, the embedded DRAM. So this one is integrated on the same die of the processor, like your CPU or GPU. So it is typically used for the last level cache, or you may use it for the global buffer for your machine learning accelerator. For example, like the Google's CPU, you can use eDRAM, for example, as a global buffer. So the eDRAM tries to bridge the gaps between the SRAM and DRAM in terms of the speed, the power, and density. And eDRAM, if you look at the specs, in terms of the random access speed, it's somewhere between the DRAM and SRAM. For example, SRAM, we know you can get the data in 1 nanosecond. And DRAM, you may need like several tens of seconds, let's say 20 nanoseconds to 40 nanoseconds for the row cycle time. And eDRAM, typically, let's say 2 to 3 nanoseconds. So that is the target for the eDRAM. And in terms of the cell size, if you normalize that to f square, and SRAM, you know, is like larger than 160 f square or even to like 300 f square. And DRAM, you know, we discussed typically is 6f square. Of course, in the recent nodes, like recent 2 or 3 nodes, then it increases a little bit. But then generally, it's like around 6f square. And eDRAM is somewhere in between. It's like 330f square to like 60f square, in that range. So this is the target for the eDRAM. And the eDRAM is commercialized by the IBM, and IBM used to make good eDRAM with the SOI technology. This is a silicon on insulator technology. So the substrate is like silicon, a very thin silicon on the oxide. So here, this is an example from the IBM. This is at 45 nanometer node for the eDRAM. And the eDRAM, again, in this case, for the IBM's implementation, is still 1T1C. The circuit schematic is the same as the standalone DRAM, like one transistor, one capacitor. And in this eDRAM, it's a trench-based capacitor. So you fabricate this trench first. You dig a trench into your silicon substrate, and then you make the capacitor first. So then you make your transistor here. This is your transistor, and then you have your capacitor here. So you make the transistor first, then the front-end logic process will not be impacted. That means you can still follow the same procedure to fabricate your logic transistor. As a trade-off here, because you use logic transistor to function as this access transistor, then you may have one downside for the 1T1C cell. So can you imagine what is the problem if you use logic transistor here as the access transistor for the DRAM cell? Leakage, right? So because we discussed before, the standalone DRAM access transistor is specially engineered with this recessed channel to reduce the leakage to like femtoM level. But if you use the normal transistor, like the access transistor, the retention time you see here reduced to like 45 microseconds. So you know DRAM standalone should be like more than 64 milliseconds, right? And this one reduced to like tens of microseconds. So the retention time is much reduced. That means you have to refresh the DRAM much more frequently in this case. And here are more details. on the IBM's 45 nanometer eDRAM cell layout. And here the layout is not that compact. And this is one unit cell. So you may have the 1T1C here. And this is the transistor, and you have one side connect to the BL, the other side connect to the storage node capacitor, and that storage node capacitor needs to be embedded underneath the substrate. It's a trench. So here the design rule is more like a logic design rule. Therefore, you have many spacing between. And then the cell size in this case is about 32F squared. So you cannot squeeze that too much because it follows a logic design rule. Because the whole process needs to be compatible with the logic fabrication. So IBM likes to use the eDRAM because IBM's product, is this power series microprocessor. So IBM business model is to build the data center, right, for the business customers. So they try to build the data center using their own processor, and they have a power series processors. So I believe the latest one is the PowerLine that was introduced in 2017. And this year, they're supposed to release the Power 10, the latest one. But I haven't seen that yet. It's on the news article, but the details are not released yet. So the available one is this PowerLine. So this PowerLine processor is fabricated in 14 nanometer FinFET, and IBM is a partner of GlobalFoundries. So the fabrication is done in GlobalFoundries, at least for the PowerLine. And for Power 10, IBM switched to either Samsung or TSMC because they want to switch to 7 nanometer process, and GlobalFoundries cannot do that. So here, for the eDRAM cell size, the Power 8 is on the 22 nanometer planar SOI platform, and then the cell size is this one, and then the power line is this one. And if you normalize to the technology node, if you think that is the F, as we discussed, this is not a good correlation. But if you still use that to normalize, then the cell area will be like 54F squared or 89F squared. So it's still smaller than the SRAM as a same technology node, at least 2x or 3x improvement of the density. So that is the density for the eDRAM. So for the IBM's processor, the eDRAM is used as a last level cache. So in their case, their L3 cache is eDRAM. So in IBM's processor, then the L1 is still your SRAM, L2 is SRAM, and L3 becomes this eDRAM. And this eDRAM can be much larger in terms of the capacity. So for example, in this eDRAM, if I recall correctly, they may have like 128 megabytes kind of eDRAM on chip. So this is larger than any SRAM cache. The reason is that at the same chip area, the eDRAM is like 2 times or 3 times higher density than the SRAM. So you can use eDRAM to replace the last level cache. But you cannot do that for the L1, L2. Why is that? Any idea? So eDRAM has higher density. Why don't we replace L1, L2 with eDRAM? Any idea? eDRAM here, the root cycle time 2 nanoseconds. You cannot do too much about it. So the L1 certainly, for the IBM's processor, it has very high clock frequency. I believe it's like 5 gigahertz. So that means 200 picoseconds, like the clock. So only SRAM can achieve that. So eDRAM cannot do anything below like 1 nanosecond because you have such cap to read out. And this graph shows the scaling trend for the eDRAM technology from IBM and GlobalFoundries. They do have just several generations. And then this is the latest one for the power line processor. And then Intel also at one time tried to commercialize eDRAM. So they presented some research papers at their 22 nanometer FinFET platform back in 2014. So their approach is a little bit different from IBM's. So in this case, they use a stacked capacitor for the eDRAM. So it's still 1T1C, but you have the transistor here, and then you have the capacitor on top. So they call it a capacitor over bit line architecture. So basically this is the same as the stacked capacitor used in the standalone DRAM. And Intel managed to do that on the 22 nanometer FinFET platform. And here are some specs for the Intel's eDRAM. So it can achieve like 3 nanosecond to 5 nanosecond readout speed. And then the retention time is hundreds of microseconds. So this is still much shorter than the standalone DRAM data retention time. Because here, again, you use logic transistor as an access transistor, then the data retention will be worse. But after those two demonstrations, Intel didn't continue this effort, so this is not in the production. So looks promising, but I don't know. Maybe there are some other challenges in the manufacturing or the yield. Then this was not in the volume production. And then I will introduce a few more advanced concepts to build the eDRAM. This is still in the research stage. The first one is called this 1T floating body eDRAM. So in this case, we get rid of that capacitor. So the whole cell is just one transistor, but this transistor is on the SOI platform. So here the SOI is silicon. This is the silicon on top of the so-called buried oxide. So this is silicon on top of the silicon dioxide. So you have a thin body here, a few nanometer thick silicon. This is your substrate, and this is the SOI technology, like the IBM, GlobalFoundries, and also Samsung may have this kind of a process. So the idea is simple for this one. So here the idea is to introduce the holes in the substrate. So you can apply some large voltage between the source and the drain, and then you will have the electrons travel through, and then there will be so-called the impact ionization process to generate the electron and hole pair. And we have discussed a few times about the electron hole pair generation. So here, if you have large current, and then the electrons may transfer the collected energy from each other. So one electron may generate more electrons. So this is called the impact ionization process. So as you generate one more electron, then you will get one more hole, because the electron and hole will be pairs. So electrons will be collected to the drain, and holes will be left over in the substrate. And we discussed before, if it's a bulk process, the holes will try to sink to the ground. Typically, the body is ground. But in the SOI, because the body here is insulator, so the holes will have nowhere to go. Therefore, the holes will be accumulated in this region. So the channel potential is raised up in this case. So if you write the data in, it's like you generate the holes, and holes will be accumulated in this region. And then later when you read out the current, then for this case, you will have higher drain current if you have holes in the floating body. If you don't have the holes in the floating body, then you have less readout current. So you use the holes. Those are accumulated in the body as the mechanism to store the data. This is a DRAM because those holes cannot be there forever. After a certain period, the holes will be recombined with the minority, will be recombined with electrons, the minority electrons in the substrate. So this can last for some time, and then you can use that as an eDRAM. So this is still in the research stage, not in manufacturing yet, but this can be more compact because you only need one transistor, you get rid of the capacitor. And what is more interesting would be this 2D GaN cell. This is also under the research, and actually, my group, also Professor Arijit and Professor Sumandata's group, are actively working on this. So the idea is straightforward. So you can have two transistors to function as a GaN cell. You can use this for the eDRAM on chip. So here you have two transistors. One transistor is the reading transistor. The other transistor is the writing transistor. So here you have some write word line and read word line, and they have write bit line and read bit line, and they share a common source line. And your storage node is here. This is your storage node. So what you can do here is to charge up this storage node by the writing transistor. You inject the charges. Let's say you inject the charges. You can think like a positive charge. It's not whole. Let's say it's just positive charge. You can have positive charges here. And then this can effectively turn on the reading transistor if you inject the charges from the writing transistor to the storage node, because the storage node is a gate cap of the reading transistor. So if you have charges on this cap, then the threshold voltage of this reading transistor will be lowered. It's like you apply positive voltage on the reading transistor. So you can have larger readout current. But of course, those charges will not stay there forever, right? And it can leak out, for example, through the subthreshold current of this writing transistor. So this is an eDRAM because you cannot sustain the charge for a long time. However, there may be some tricks to make this retention time much better. For example, here is writing transistor. If we change the channel of the transistor to be the oxide channel, semiconducting oxide channel, and then this leakage can be much reduced. So here, this is our invention for the future. So you can have the reading transistor as silicon transistor at the bottom, and then you can build the writing transistor on top using this green material. This green material will be some oxide channel. Oxide. And in particular example here, you can have this oxide to be like those oxide. IgZO is Indian gallium zinc oxide. IWO is Indian tungsten oxide. So the good features for this oxide channel is their leakage current is so low. So the leakage current can be like a femtoan approaching like the DRAM standalone DRAM access transistors leakage. Even less than that, femtoan to like attoan So this is 10 to minus 15. This is 10 to minus 18. So you may have very low leakage through those oxide channel transistors. This oxide channel, the mobility is low and the band gap is large. Therefore, the leakage is low. And then in those demonstrations, I believe there are two papers, one from IBM, one from IMEC, one from Professor Sumandata's group. So then you can get the retention time pretty long, like 10 to power 7 millisecond or 10 to power 3 millisecond. So this is even better than standalone DRAM. So this can be a good candidate for building the DRAM on chip. So those materials like IGZO is not new, I would say. So actually you have the IGZO transistor on your product on your mobile system, because all your display, like your LED, OLED display, all the display, each pixel is controlled by the IGZO access transistor, or the photodiode, the image sensor, in the LED, are all controlled by the IGZO. LED, I would say the LED a diode is controlled by the IGZO display transistor. The reason is that IGZO is transparent. The band gap is high. Like this material, the band gap is like maybe 2 to 3 eV. So that is transparent under the light. So that's why you use for the display control circuitry. All right, so here are some advanced topics. Of course, I will not require that in the exam. This is just for your interest. So here, this is the final summary. For the DRAM, we know that for the larger capacity and higher bandwidth, we must do this HBM by the 3D TSV. And also for high performance applications, the embedded DRAM compatible with the logic process is a very promising direction to pursue. This is more and more important today for the high performance computing, because we need a very large cache on chip, and SRAM cannot do that. So if we can use DRAM, embedded DRAM, to do the last level cache, then we can improve the system performance, because this one has much larger capacity than the SRAM. So this is very useful for like machine learning accelerations. And then here, I would say there's no memory, neither the existing memory or emerging new memory, that can combine the benefits of the DRAM in terms of speed, cost, and endurance. So I would say, if you ask me what is the future of DRAM, the answer will be DRAM. There's no replacement for DRAM in the system. So there's no new technology that can completely get rid of DRAM. DRAM will stay there forever. Let's say as far as I can see in the system. So there's no technology that can replace DRAM at this moment. So this is like the summary for the DRAM. Any questions? This DRAM section. So there's one question. For the eDRAM, F does not strictly stick to the physical dimension. So the F is like the, so here, because in the slides we use the technology node incorrectly to normalize the eDRAM density. So the F is the same as the technology node in our slides. So it does not correlate with the physical dimension. That is true. What do we mean by endurance? Okay, we will talk about that in the next section on the flash, because this is a problem for the flash. for the non-volatile memory. So endurance, simply speaking, how many cycles you can write the data into the cell before it fails. And the SRAM DRAM has no such issue, so that's why we didn't discuss it. But in the flash, starting from the next lecture, we will talk about the endurance. It's an important aspect for the reliability of the memory cell. Okay, let me stop here for the DRAM.